Hey guys, no lead code today. I'll be talking about Malloc. So this is a function call in C provided by the standard library. It is probably the most important function call in all of C. It teaches you a lot about OS memory management and a bit about the system calls that happen behind the scenes. I'll be getting to the system calls later. Now here I have a process. So the code, the instructions, the data, the instructions. What we'll be focusing on is the heap and the stack. The stack of the process is allocated by the OS. Alright. Now for the heap is considered dynamically allocated memory. And what does it mean to be dynamically allocated memory? So your amount of memory that you're going to be using is not going to be known at compile time. That's what it just means. It is basically resizable if you think about it. And it's kind of like, you know how you would ask a user for some input n, and then you would make an array of n size, and then you would insert n things into it, items into it, right? And you would not know what n is at runtime, but that's how it would basically be dynamically allocated. All right. And the way in C, when you have dynamically allocated memory and when you call malloc or calloc, right, it's up to you to free, like call the free, otherwise you would have memory leak in your programs. And that's why in Python it doesn't really matter, everything is stored on the heap, but they have a garbage cleaner for you. That's what they call it, garbage collector, garbage cleaner. Don't know the exact name, but in C, if you do call these memory allocating functions, then it's your responsibility to also call free on them, otherwise you get leaks. And yeah, now about heap. What is malloc doing under the hood? First I'll talk about heap. If you think about heap, right, what I want you to think about for heap is, imagine it as a linked list, okay? And the nodes inside of the linked list represent some bytes in memory. So let's say if we had 16 bytes, then the node holds 16 bytes, like a chunk of 16 bytes, like this in memory, right? Something like this. That's how it would look like drawn out properly. And it would hold 16 in that. Now, when you call your malloc and you say, I want 16 bytes, it doesn't just take a node, right, and say, okay, these 16 bytes have now been allocated, are now going to go into this node. It doesn't do that. It does 16 plus some metadata. Now, what is this metadata? All right. The metadata, I would say the most crucial part of the metadata is the free. So there is a bit in here that tells it says that, is this block being used by the user in memory? Is it or is it not? If it is free, then you can store the 16 bits onto this, right? If it is not free, then it is preoccupied, and you should jump to the next node to see if it is free. If not, then jump to the next node, right? And that's how heap essentially works. The free is the main part, I would say. There's algorithms as to, I'll talk about the algorithms shortly, but there's ways to, and by using this metadata, there's ways to understand how making it more efficient to allocate the memories, basically. Now, if you have this, right, and you have this linked list, the issue with having chunks of memory reserved, right? So let's say you have a fixed 16 for every single node. The issue with having a fixed 16 becomes that you ask for 16, right? You'll always get 16. But if the user only puts in 4, then they've wasted 12 bytes of memory. So you could say, if they wanted to write a string of 16 characters, but they only wrote a string of 4, the rest of the 12 characters are now getting wasted. And you could have these 3, or you could even have 4, right? And if you had 16 bytes in memory, if we said a hypothetical size of, let's say, 64 bytes, and you have these 16 bytes to show for it, these chunks of 16 bytes to show for the 64 total, then right now we are using only 4 times 4, which is 16 bytes, right? But the amount you're wasting is actually 48 bytes. So you see how, and like if you call Malloc, right, and you said, okay, now since I know that there's 48 bytes free, hypothetically I should have another chunk that I should be able to use, but there's only 4, and all of those 4 are filled up. So the Malloc will fail. It will say, no, I have no memory. And this is called fragmentation. It's basically like having holes in memory, so you haven't used the entire chunk. What you've used is only a little bit of it, and this has led to wasting a lot of memory. Now how do we prevent this? All right, there's a couple of algorithms that talk about how to minimize this. One of them is being powers of 2. So if we had the chunks be in powers of 2, so 64, then the 64 would break into 32, 32, then we would break this into 16, 16, this into 4 and 4. So if we see that the user is only using 4, right, or if the user wants to get only 4, then we would start breaking it down from 64 to 16 and then to 4, and then we would only give them a 4 for the node. This way we are minimizing the amount of memory being wasted. You don't need to know the exact implementation details, you just need to know that this is a trick people use. The other is variable size. So if we have nodes of uneven bytes, let's say one was holding 16, one was holding 32, and one was holding 24, then if we asked for, there's 2 terms, best fit and the worst fit. Now the best fit is, if we asked for 4, then the absolute difference between 16 minus 4, 32 minus 4, 24 minus 4, obviously 16 minus 4 is the least, because it is the least farthest away, right? And we would say that the best fit, so to put the 4 bytes of memory, it would be best to put it in the 16 byte chunk, right? So closest in size. And the worst is the direct opposite, the farthest in size. So this is the worst if you had a size of 4, and this was the best, biggest difference in size. Alright, these are the 2 ways. Like, you don't need to know much more than this, I would say, for operating systems. Now the other thing about heap, right, is, yeah, I talked about this, so I'll talk about the list in a bit more detail. The way your operating system works is you will basically traverse through this list, right, and you'll ask if it is free, if it is free, if it is free. If not, then it will jump to the next node, it will jump to the next node, it will jump to the next node, it will jump to the next node. Think of it as a linked list. Wherever you find the free, you'll allocate the chunk. And if you hit the end of the linked list and you never had anything, then what it causes is a BRK or a SBRK system call. This basically is a system call that traps to the OS, and it causes you to take up more heap. So they'll basically give you extra heap size over here. Soon you'll get these circles of memory. Now there's two ways to get this extra bit. If that fails, right, then you can still also call map. This is another system call, but this one gives you a complete page. So page is different from the heap, but you could model it the same way. I haven't experimented with map, I've experimented with sbrk, but you would basically get a completely new page that you can change it manually. Besides that, there is nothing more to Malloc. Remember to free your allocated memory. There's always metadata that is stored, so it's not always only 16, it is 16 plus some bytes that are used to store your metadata. That could, some of this could also just be the size of the chunk. It could be the next pointer, right? Because that is how the linked list works, right? The metadata will hold the next pointer, whether you're free or not, right? And a magic number. Sometimes they have a magic number in there. This is for debugging. It is optional. And then I talked about fragmentation, right? Remember fragmentation? It is gaps in memory. So you're basically wasting memory. You asked for some and then you have these holes, as they say. Now the way to avoid it is to use powers of 2 chunking, right? 64 to 32 is 16 to 4. Then there's the best fit, the worst fit, and then expanding the heap via brk, sbrk, and anonymous map. This returns an anonymous page, as they call it. And that's it for today.